Today we're going to look at limits at infinity. So for these first two problems with the graphs, go ahead and do them on your own. When you are finished, you can unpause the video and check your work. So looking at the first problem, we're given the graph of the piecewise function shown below, and we want to find the limit of each of these. So the first one says the limit as x approaches negative infinity. So that means as our x values get larger and larger in the negative direction, where is our graph going to be moving? So if we look at this, you can see that your graph is approaching, it looks like it has a horizontal asymptote at y equals 0. So I would say 0 in this case. For the next one, the limit as x approaches negative 2 from, and it has a minus sign right there, so remember that means from the left. So if we were to draw a line right here, remember that this is the right side and this is the left side. So as we're approaching negative 2 from the left, that would be over here, we can see that our y value is approaching 2. As we are approaching 2 from the right side, we are up on this part of our graph, and you can see that the y value is approaching 3. Since the left and the right-hand limits are approaching two different values, that means that the double side limit, so there's no plus or minus right there, does not exist. The limit as x approaches 2, this doesn't again have a left or right plus or minus next to it, so that means we want the double side limit. So from the left side, we're approaching this value, and from the right side, we're also approaching that value, and so that y value is equal to 3. And the limit as x approaches infinity. So as we're getting larger and larger x values, it looks like our graph is going down this way. So it looks like it's going towards negative infinity. Now we know that technically negative infinity is not a number, so the limit doesn't exist, but we are still curious as to where the graph is going. Is it going to positive infinity or negative infinity? So instead of writing does not exist, now we're going to go ahead and write negative infinity. But if you were to write does not exist, it's not incorrect. But again, we still like to know where it's going. So now, from now on, we're going to go ahead and write negative or positive infinity for those. Looking at the next ones, we have the limit as x approaches negative infinity. So that would be our graph going this way. And it looks like it has an asymptote at y equals 2. So I would say for this first one that we are approaching this asymptote at 2. For the next one, we have the limit as x approaches negative 3 from the plus side, means the right side. So where is negative 3? It's right here. This is x equals negative 3. And we are looking at what happens on our graph from, again, this is the left and the right. So from the right side would be this portion of our graph here. So you notice that the y values are approaching 2. For the next one, we are looking at the limit as x approaches 0. So from the left and the right, so the left side is approaching this value and the right side is approaching the same value, which in this case is a y value of negative 2. K of 0 is not a limit, so that is just asking for what is, when x is 0, what is the y value? So when x is 0, notice that we have this closed circle up here. So that means k of 0 is equal to 3. Looking at the next one, we have the limits as x approaches 2 from the left side. So here's 2. From the left side, notice that my graph is going up, the right side is going down, but we just want the left side, so that means we're going to go ahead and say it's going towards infinity. Again, it does not exist, but we want to know that it's going towards infinity, so instead of writing does not exist, now we're going to write infinity or negative infinity. So if I were to look at the right side, the limit as x approaches 2 from the right for this function, I would say it would be equal to negative infinity. But if I were to write the limit as x approaches 2, because the left and the right side are both going different directions, that one I do have to write does not exist. Looking at the last one, we have the limit as x approaches infinity. So as x approaches infinity, you can see your graph is going this way, and it looks like we have an asymptote here at -1. So this would be -1. So that's graphically looking at finding the limits with some of them, a couple of them had infinity in there. So let's go ahead and look at these problems without the actual graph in front of us. So if it's a rational function, we can use the rules that we learned for graphing rational functions and finding the horizontal asymptote, because remember, the horizontal asymptote tells us the end behavior of our graphs. So for this first one, I know that this is a degree 1 over degree 1. And for our rational functions, we said when the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote would then be the leading coefficients. So both of them are 1. So that means this has a horizontal asymptote at y equals 1. So that means the limit as x approaches either positive or negative infinity would be approaching 1. In this case, we're going towards positive infinity. You could, of course, also confirm that using your graphing calculator. So if I go ahead and plug this into my y equals, I would just want to make sure to put parentheses around anything in the numerator denominator that has more than one term, such as right here, the denominator has 2 terms. So if I go ahead and I can look at the graph, actually do a standard window, zoom 6 is a standard window. So if I look at the graph, it's kind of hard to tell, but if I were to hit trace and trace along my graph, I can see that in the long run, it's approaching a y value, because you can see there keep going up of 1. So rather than doing that each time, it's a lot easier if you use your table. So if you go to second window and change the independent to ask, it's going to allow you to type in values into your table. So then hit second graph, which is your table. And I can just keep on plugging in larger and larger values. And the larger and larger values that I get, notice that in the long run, they're approaching a y value of 1, because that's, again, a horizontal asymptote. And even if I were to do the negative direction, negative, very large negative values, you can also see that it's approaching a y value of 1. So if I go back to my graph here, remember that for this rational function, there's actually a vertical asymptote at x equals -9. That's why this part of the graph is going down. So if I were to zoom out to get a larger graph, I'm going to go over here and just zoom out. You'll see that it's that asymptote, but the end behavior of your graph follows y equals 1, the horizontal line. So that's why that's the limit. So if I look at the next one, same thing. This is a rational function, so we can use what we learned for rational functions in order to help us find the limit as x approaches infinity. So the degree of the numerator and the degree of the denominator are both squared. So degree 2 over degree of 2 means that we have a horizontal asymptote at the leading coefficients, which in this case would be 3/4. So that means that the limit as x approaches infinity is going to be approaching 3/4. And if I were to, again, look at this graphically, you could also confirm that using your graphing calculator if you want to plug it in. Looking at the next one, we have a degree 2 over degree 4. So when the numerator degree is less than the denominator degree, remember that the horizontal asymptote is at y equals 0. So that means that this graph in the long run is going to be approaching 0. And again, you could also confirm that graphically. Like I said, just make sure you put parentheses around what's in your numerator and denominator when you do so. Looking at number 4, for this one, this has a degree 2 over degree 1. So that means that there is no horizontal asymptote. Remember, that means that we have some kind of other asymptote. In this case, we have a slant asymptote. And you can use those first terms to help you determine what the degree is going to be, and also looking at the coefficients to determine if it's a positive or negative. So if I just look at those first terms without even having to do the division, I have 9/5 and x squared over x is just x when you divide the terms. So let's go ahead and actually write that out. So if I just write out 9x squared over 5x, that's equal to 9x over 5. Notice this is linear, and it has a positive leading coefficient. So something that's linear means that it's going to go up to the right and down to the left. So if I'm looking at the limit as x approaches infinity, that means that this is going to be going towards infinity. If I were to do negative infinity, it would be going down towards negative infinity. So let's go ahead and look at this graphically. So we've plugged into our y equals, and I can look at the graph, zoom 6 for a standard window, and you can see that as we go towards infinity, your graph is going up towards infinity. If we were going to negative infinity, it would be going down. And then in your table, if you wanted to look at that, you could just plug in larger and larger values. So if I plug in larger and larger values, you would see that the y values just keep getting larger and larger. They're not actually approaching some value. So right here, if you click on this, remember when you see that e, that means times 10 to the 7th power. So that would be moving that decimal place to the right 7 times to get this value that we have right here. And again, you could just keep on plugging in larger and larger values to see that the number is going to get larger and larger. So infinity for the next one. So for number 5, if I look at this one, same thing. I can look at the degree of the numerator versus the degree of the denominator. So we have a degree of 5 and over a degree of 4. And if you remember to always make sure you're in standard form. If you're not, you want to put it in standard form first. So for this one, again, I'm going to look at those first terms to help me determine where my graph is going to go, because that's what you'd be dividing. So if I divide 2x to the 5th over 8x to the 4th, that gives me 1/4 x. So that means it's going to go up to the right and down to the left. And then again, you could plug this into your graphing calculator to confirm. Okay, so I plugged it into my y equals, and if I hit graph, you can see that it's going up towards infinity this way and down towards negative infinity if you're going to negative infinity. So you could even zoom out to even get a larger view of the graph, just to even see. But and even if you don't want to use your graph, you can plug in larger and larger values into your table. So if I go to my table and look at larger and larger values, you can see larger and larger values give us larger and larger y values, which means we're going towards infinity. So looking at the next one, this is not a rational function. So if it's not a rational function, you would probably want to plug this into your calculator to look at the limits. It's very similar when you have a radical in your equation to be like a rational function. So really, if you look at the highest degree term, 9x to the 4th over 4x cubed, because we can actually figure out what this is equal to. The square root of 9x to the 4th is really equal to 3x squared and over 4x cubed. So this tells me that the degree of the numerator is going to be smaller than the degree of the denominator, which means there should be a horizontal asymptote at y equals 0. So even with the radicals, I can still tell that. So I actually know this is going to be approaching 0. But like I said, if you don't know, let's go ahead and plug it into our calculator. So if I plug this into my calculator and I look at the graph, you can even see that it looks like the graph's approaching 0 right here. It's kind of hard to tell, but you could always zoom in, or you could plug in values. So if I plug in larger and larger values for x, notice that it's going to be approaching, it looks like 0. So remember that if you see 7.5 e to the 4th, remember that's 7.5 times 10 to the 4th power, negative 4th power, sorry, it's negative 4. So that means you're moving your decimal place this way 10 times. So really that number that we get not 10 times, sorry, 4 times because it's to the negative 4. So 1, 2, 3, 4 would be here. So that means that it's just getting closer and closer to 0. So if I did an even larger value, notice we get negative 5 times 10 to the negative 5 power, negative 5th power. So if I plug in even larger number, same thing. So notice it's just going to get closer and closer to 0. So that's why we are approaching the value of 0. And looking at this last one, for this last one, this is not a rational function. So this is an exponential function because we have a variable as an exponent, and we can use our calculator to help us, or we can just think about our graph. So if I have negative e to the negative 4x, you can think about your parent graph. So this would be y equals e to the x. And what's happening to our parent graph. So we are reflecting it across the y-axis. So if I were to reflect this across the y-axis, because that negative right there, and then we are going to horizontally compress by 1/4 because of that 4, and then the next one would be the negative on the outside, which is going to reflect across the x-axis. Confirm. So we just plug that in, and remember to get the e again at second, and you can use the division symbol. So now that I have this plugged in, I can hit zoom 6 for a standard window, and you can see that the graph looks like the graph that we drew. It's kind of hard to see that line right there, but you could always zoom in to confirm that it's going this direction. But again, we're only looking towards negative infinity, and as you can see, as your values go towards negative infinity for x, your y values are going down. And you can confirm that by plugging in larger and larger negative values. So because we're doing something exponential, if you plug in something too large, it's going to give you an error just because your calculator can't compute something so high. So we're going to have to pick something else. So if I do negative 100, still too large. So let's do negative 50, see if that works. So if I do negative 50, you can see that's a very, very large number. We have negative 7.2259, etc., times 10 to the 86th power. That means I'm moving this decimal place to the right 86 times, which is a very, very large number. So your graph, again, is exponentially decreasing at that value really fast. And again, so that's why sometimes if you try to plug in values that are too large, your calculator just can't compute it because it's just too large of a number. And if we go to in positive infinity instead of negative infinity, you can see that we had it before, but as your x values go towards infinity, you can see your y values are going towards 0. So if the question was instead the limit as x approaches infinity for this function, negative e to the negative 4x, that would be equal to 0. And that's it for limits at infinity. So just keep in mind that even if you can't use something like with the rational functions, you could always plug it into your calculator and look at very large values that are positive or negative to find the limit.